Truck runoff ramps are built with gravel at an incline. They work as emergency ramps for trucks experiencing braking issues. And they do this essentially by taking the kinetic energy and transforming it into potential energy, and then also by kinetic friction, which takes energy from the system. Assume a semi-truck enters an emergency off-ramp going 60 miles per hour, which has already been told to us that that's 96 kilometers per hour. The gradient is built at 15% or 15 degrees incline. The truck gets 160 meters up the ramp before it slows down to a stop. What is the kinetic frictional coefficient from the truck and the gravel, which causes the energy loss in the system? So the thing we are looking for is mu k. That's what that looks like in our equation, the Greek letter mu with a subscript k to denote that's the frictional coefficient for kinetic friction. We can draw an image of this. If I do kind of like an off-ramp, this is not to scale, but we'll label this as our 15-degree gradient. And I'm going to make it bumpy to denote that there's gravel, which is going to cause friction. And here's our semi-truck going up it, our teast. The D data points, or the things I know or the things I'm given, is the initial speed of the truck, V initial. I'm going to use the 96 kilometers, and I'm going to convert that to meters per second. So it's per 1 hour. For every 1 hour, there are 3,600 seconds. And for every 1 kilometer, there are 1,000 meters. Kilometer unit cancels, hour unit cancels. I'm left with meters per second. I'm going to plug that into my calculator. I get about 26.7 meters per second in terms of what my force is going to be. And then my angle I'm given is 15 degrees. And the diagonal distance, I'm not going to call it X or Y. This is the diagonal distance up the ramp, is 116 meters. Those are really the only things I know. Oh, I also know it comes to stop. The final is going to be 0 meters per second. So that's the idea. We want it to slow down and stop. The equations I'm going to use, I want to note that work is going to be the change in energy. Work is also the force dot the distance. That's going to be helpful for me in this case. The truck slows down and stops it, so that's going to be helpful. And I know I'm going to want kinetic energy as equal to 1/2 mv squared, and potential energy as the mass, gravity times the height. And if I have kinetic frictional coefficient, I want the kinetic friction equation, mu k f n. And that should be about all the equations I think we are going to need for this. Our S for solution set, I'm going to start with the fact that I know work is equal to the force dot the distance. In this case, the force I'm talking about is the frictional force, Ffk, and this is going to be times the distance times, in this case, the cosine angle between the two. Friction is always opposing the motion, so it's always opposite the motion that it's going, so it's always 180 degrees, gives me -1. So it's going to equal negative the frictional force times the distance. And then if I think about the frictional force, I can expand this equation. It's a frictional coefficient times the normal force times the diagonal distance it travels. So it's not on a level plane, right? So the normal force usually counteracts gravity if I'm on a horizontal surface. This isn't a horizontal surface. To understand exactly how this normal force is on it with respect to gravity, I'm going to draw the free body diagram. I'm going to draw the free body diagram. Gravity is always pointed straight down. So this is Fg. I'm actually going to write it on this side. See why in just a second. F G, and then the normal force because of the incline is at this angle. And I'm going to draw a line like this. This is 15 degrees, okay? This is the normal force, and then this is the frictional force, FK. Now, to make this problem simpler, because I like the idea of one of my vectors being in 2 dimensions rather than 2 of them, I'm going to rotate it clockwise by 15 degrees. Just so I can kind of note, I can get a relationship for this normal force. It is equal to this this component of the gravitational force. And in this case, we could call it the y component, or just this little section of the component, which you'll notice is the side that's adjacent to that diagonal. So I can say that the adjacent side, so this this side here we'll call F, G, Y to denote it's the component. That is going to be equal to, so F, G, Y is going to equal F, G cosine 15. And this is what equals the normal force. So the normal force, because it's directly countering the normal force, that's going to equal, well, the gravitational force is just the mass times gravity, and then this is times cosine of 15. So that's what I'm going to substitute in for this normal force. So I get the frictional force is the frictional coefficient times the mass times gravity times the cosine of 15 degrees because of that gradient. Then I am going to essentially multiply that or put it back all into the work equation, right? Sorry, I'm a little backwards in where I'm going with this, but work is equal to the negative frictional coefficient. We have mass, gravity, cosine of, I'm just going to keep it as 15. I plugged it in now. You can plug it in now or at the end. And then times the distance. That's our first work expression. The other work equation is going to come from the fact that the energy changes. So, and always that's represented as final minus initial. So final energy and the initial energy is going to be a combination of gravitational potential plus kinetic. But we're going to talk about that a little bit conceptually. Like at the beginning of the system, when the truck is at the bottom of the ramp, it has no gravitational potential energy. That is 0. And then at the height where the truck stops, it has potential energy, but it no longer has kinetic energy because it stops. So my second work expression is going to be the final potential energy minus the initial kinetic energy, which is going to look like the mass, gravity, the height it gets to, minus 1/2 the mass and the initial velocity, which we know we're given. And I can pull out the mass. I'm left with gravity, h minus 1/2 the initial squared. And this height, that is something I don't know. I do know that it travels a diagonal distance of 116 meters. With respect to the height, that's this part of my right triangle here, which we'll note is the opposite side of the angle. So the height, if I look at sine of 15 degrees, that's going to be the opposite. That is the height. Over the hypotenuse, that's the diagonal distance it travels. So I'm just going to solve for height. Height is going to be the diagonal distance times that angle, the sine of 15. I'm going to plug that in there. I get work is equal to mass, gravity. Instead of writing height, I'm going to write diagonal distance, sine 15 minus 1/2 the initial squared. And then these two expressions, I can set equal to each other. So in the one case, I have negative mu k, or frictional coefficient. That's the thing we're looking for. Mass, gravity, cosine 15 times the distance, which you'll notice doesn't technically matter which one we put first. If it's multiplication, order's the same. This is equal to the mass, gravity, distance, sine 15 minus 1/2 the initial squared. The mass units cancel, which is good because we don't know actually the mass of this truck. And then I want to solve for our frictional coefficient. So I get mu k is equal to, we can distribute this negative. This negative is mainly direction based. Frictional coefficient is always going to be positive, but let's keep it for now. It's going to have this gravity distance sine 15 minus 1/2 v initial squared all over. I'm just essentially dividing all of those to the other side. So it's going to be gravity cosine 15 times the distance. Now, could I simplify it a bit further? Sure, but it's sufficient enough as it is there. Let's scroll down just a little bit and plug in our numbers. To the last part of this. If it's a kinetic frictional coefficient, I want all the units to cancel. So mu k, that's going to equal negative 9.81 meters per second squared times my distance of 116 meters times the sine of 15 degrees minus 1/2. This is the 26.7 meters per second squared. I have meters squared per second squared minus meters squared per second squared in the numerator. That's good. Can only combine like terms, so the units need to be the same. That's good. 9.81 meters per second squared in that denominator. At the cosine of 15, and then that diagonal distance again, 116 meters. I'm going to have meters squared per second squared in my numerator and meters squared per second squared in my denominator. The units do cancel. So that looks good. Looks like we set it up correctly. When I plug that in, I get 0.056 unitless, which would be the frictional coefficient between the tires and the gravel, which would be enough to kind of slow the car down. Otherwise, the truck would go further, right? If friction weren't slowing it down somewhat, right? And gravity is still slowing it down just by the nature of transforming kinetic energy into potential energy, but the friction is slowing it down even more. It's not going to go quite as far.